everyone. You can hear me. My mic is on. Okay, good. Mm. So welcome to this uh, e-learning about permanent deformation e-learning package, and there is and greetings from the central Finland. I am on the road at the moment here, sitting in the survey van, talking to you. So we are we are uh, we are doing like a drainage inventory measurement. So as we heard a week ago, you all know that drainage is very important. Okay, the e-learning permanent deformation e-learning package, it's divided in 7 lessons, and the lesson 1 is what's permanent deformation and why don't we like it? Why we don't like it? Permanent deformation in ideally elastic material, it's like totally recoverable, and meaning that if the stress is taken out, then the material it returns back to its original shape. And but however, road construction materials, they are not ideally elastic, and they will accumulate some permanent deformation as a result of every load application. And here you can see the diagram that the response to heavy wheel load, it's always a combination of some resilient deformation and then a small proportion of permanent deformation. And when the stress is relatively low and relatively far away from the strength of the material and the failure stress limit of the material, then the at start of the loading, the strain increment, it's first high due to the initial compaction but of the aggregate, but then soon it will settle down and stabilize to a constant level. But on the other hand, if the stress level is high and it's close to the strength of the material, the failure stress level for the material, then the strain it keeps accumulating continuously, and it's not stabilizing anymore, and the rot increase, it keeps on increasing. So problems, what kind of problems permanent deformation causes? First of all, traffic safety issues. The ruts on the roads, they collect water and give there's risk of aquaplaning, and then different kind of deformations and bumps and settlements on the road. For example, they cause warping of trucks and unhealthy vibrations to truck drivers, and other traffic safety issues, risk for accidents. Reduced bearing capacity, it's kind of first of all, low bearing capacity is like a reason for the permanent deformation to take place, and on the other hand, when there's a permanent deformation on the road and damages and ruts and so on, then it gives again more. It accelerates the rutting. Higher road user costs, for example, higher tire costs and increased fuel consumption due to the uneven road and the ruts, and higher road owner costs as well, as I already mentioned and showed. The ruts in the road on the road, they collect water, and that together with the traffic, it accelerates exponentially after the ruts start to collect water. Then the damages on the road also start to increase exponentially. The lesson number 2, it gives more detail some idea of the stresses and strains in the road structure. And here on the left, you can see the diagram of stresses and strains under a moving load on a smooth and even road surface. There is compressive and tensile forces involved, and vertical, horizontal, and shear stresses. And then on the right hand side, the effect of an uneven bump and how it loads the pavement after the bump, and the oscillating load levels after the event. It can be much higher than the constant loading the road. And with a traffic speed of 80 to 100 kilometers per hour, one bump on the road, it can have an effect on the pavement for almost even 200 meters, and you can even see from here in the picture the locations where the truck's suspension hits down after the bump. So the effect of one bump can be very long on the road. And then the road construction materials, they follow like a viscoelastic behavior. They are not. They need some recovery time after they have been loading, and here in this picture you see 2 aggregate trucks and truck and trailer combinations passing the Koskenkylä Perko station in Rovaniemi in Finland, and their effect on the dielectric value in the poor quality subbase, and the material response follows typical viscoelastic behavior. There is a truck number 1 first rising the pore water pressure in there, and then the second and the trailer of the first truck. Then there's a little bit time to recover, but not enough before the second truck and trailer comes, and it gives typical also like shows the typical pumping effect. And in this example, it needs 18 seconds time to recover back to original level. Then the key step in improving the condition of road suffering from permanent deformation, it's a precise and reliable problem diagnosis. And the structural quality of road, it's defined by its so-called weakest link. Here on the figure on the left, the weakest spot is located in the subgrade level, and it has the structure has the risk for mode 2 rutting, and on the right the highest risk is here in the unbound structural layers, and the risk is for mode 1 rutting. And those examples in that previous slide and this one here, they are taken from the ROADEX pavement stress and strain calculation demo. That there is the direct address shown here, but there is a link to that demo in the end of the lesson 2 of the eLearning package, and there you can change the tire type, single or dual, and the tire pressures, and then pavement structure and subgrade modulus and thickness for the pavement and structure, and you can see right away the effect, how it affects on the stresses and strains and the overall bearing capacity of the structure, shown with these arrows and rectangles. The lesson number 3, it presents the permanent deformation rutting classification according to ROADEX project. And first, mode 0 rutting, it takes place through the compaction of the non-saturated materials in pavement structure, and in practice some level of mode 0 compaction always takes place in the road structure after its construction. And normally the construction compaction prior to trafficking, it's sufficient to prevent further compaction under trafficking. And this mode of rutting is usually self-stabilizing. In other words, the compaction that happens prevents further compaction. And it also causes the compacted material to stiffen and thereby spread the load better. Then mode 1 rutting, it happens in weaker granular materials where local shear stresses occur close to the wheel. So it takes place in the top part of the structure. It gives this dilative heave immediately adjacent to the wheel track where the granular material deforms. And here you can, on picture on the right, shows the difference between the mode 0 rutting here, the compaction, and then the mode 1 rutting, which is deformation of the granular materials. Here the picture on the left shows typical mode 1 rutting problems on paved road, and then picture on the right, there is a gravel road suffering from mode 1 rutting, and you can see that the interface between subgrade and structure it's relatively even, and the deformation takes place here in the upper part of the structure. Then mode 2 rutting, it takes place at the road structure. Road structure and subgrade interface, and mode 2 rutting occurs where the aggregate quality is better, and the pavement the road structure as a whole ruts, and this can be viewed in idealized fashion as the subgrade deforming, and the whole structure is like a deform bending over that. And the surface deflection pattern of mode 2 rutting, it takes the form of broad rut with slight heave removed from the wheel. You can on the left you can see typical mode 2 rutting on paved road, wide rut, and the picture on the right, it shows the GPR cross section from gravel road suffering from severe mode 2 rutting problems, and the structures are very thin on the shoulders and also in the middle of the road, and the wheel tracks, they have been rutting, and then there has been like filled over and over again new layers to those. Finally, my mode 3 rutting, it's developed because of tire wear on the pavement of paved road, or the wearing course of gravel road. So and studded tires, they are the main reason for mode 3 rutting in Nordic countries. And the mode 3 ruts, they can be identified by very sharp ruts, and the distance between the rut wheel paths than that which is normally the spacing of passenger car wheels, and it's narrower than the truck axle width. Then lesson number 4 presents a large number of different kinds of survey and monitoring techniques related to permanent deformation and investigation of permanent deformation and its reasons, such as drilling, sampling, excavations. The modern NDT techniques, they continue to make road diagnostic surveys faster and more reliable, but they will never eliminate the need for drilling and boring and sampling. Structures, they will still need to be verified, and the NDT surveys will need calibration data and samples taken for laboratory analysis. Video recordings, they give continuous record of the road, and from it can detect road surface condition, pavement distress, road markings, traffic signs, etc. And it can also be very useful aid in surveying the topography of the road and its surroundings. Video recording of the road and ditches with an audio commentary, it's also an easy way to gather basic information for drainage analysis, for example. Then pavement distress analysis and roughness, rutting and crossfall surveys, they also give valuable information about the reasons and possible remedies for the permanent deformation and different rutting modes. And laser scanner. In recent years, the greatest development in NDT techniques for road surveys have been with laser scanners, and it's a fact that these systems have become a standard tool for the various tasks in the road condition management process, such as measuring rut depths and ditch depths, ditch slope steepness, crossfall of the road, and so on. Then GPR, ground penetrating radar. It's non-destructive ground survey method, and its main advantage is the continuous profile it provides over the road structures and subgrade soils. And as a consequence, the technique it has become an important survey tool, especially on the structural evaluation of low volume roads. And further, the important advantage is that it's not intrusive to other traffic. It can be performed normal traffic speed. Then different kind of deflection measurements: falling weight deflectometer, lightweight deflectometer, traffic speed deflectometer. They provide information on the bearing capacity of the structure and stiffness, and right away directly from the measured data, many bearing capacity indexes such as SCI and BCI can be calculated, which provide information on the, for example, the location of the weakest link in the structure, and also when the deflection measurements are combined with GPR thickness interpretation, then also the modulus of different layers in the structure, it can be back calculated, and further the bearing capacity of the whole structure. And large scale of different kind of laboratory tests can be performed for the samples taken from the road, starting from a basic grain size distribution and water content and so on. Then water suction properties of the structure, frost heaves and chlorides and so on, and up to the full scale, large scale triaxial tests to give lots of information. Then lesson number 5 in the e-learning package, it presents different kind of classifications, analysis, and diagnostics, especially classification of subgrade soils and topography. And information on the subgrade soil type and the surrounding topography, it's needed initially to allow the designer to select the most suitable draining solutions and also the most appropriate rehabilitation structures. The lesson presents different topography and subgrade soil types and special things to take into account with those. And of course, drainage is one important thing to classify also, but that was already in the whole separate webinar last week. Then lesson number 6 is about managing permanent deformation. Drainage. That's always important. Then managing loading and seasonal changes. The trucks are getting heavier and heavier all the time, and I think you will hear later a little bit more about that also. And then managing the loading can be done also by setting load restriction during the springtime, for example. And then CTI, and it's an alternative way to reducing stress on the road is to amend the contact pressure of vehicles' tires on the road by reducing the pressure in the tires and enlarging the contact area. And the central tire inflation, CTI, it's the generally accepted terminology for that onboard automated system of tire pressure control that permits the driver of vehicle to adjust the pressure of tires on the vehicle while in motion. And Mode 1 rutting problems on forest roads can be managed or reduced by using vehicles with special axle configurations or by driving in varying lateral position on the road cross section. An example of first option can be seen in here picture from Scotland, where the tires of a truck have been specially constructed to be out of line or longitudinally, and they act as a roller compactor, preventing the formation of ruts. Then another option to manage permanent deformation is so-called artificial tire wander, which means that the loaded trucks are driving in different parts of cross section, which causes a specific rebound effect for the permanent deformation and reduces rutting. And this phenomenon, it's been found in Finland when testing high-capacity transport trucks with increasing numbers of axles driving exactly the same path, and I think you will hear about this also more later. Then the lesson 6 also presents a large number of different kind of structural options and different kind of structures for different kind of problems and for the problems caused by different routing modes. And there is a large number of example structures, such as adding the new layers on top, as you can see here, mix milling, using adding with new aggregates on top, and then mix milling, or also other options. The eLearning package contains also others. Then steel grid reinforcements installed in the unbound granular base cores. That's the recommended installation location inside the unbound base cores. Sometimes the reasons for the damages can be such that the only correct remedy for the problems is soil replacement, digging out the whole road structure and building new layers for the whole structure. And finally, the last 7th lesson in the eLearning package, it presents the design process against permanent deformation. There is like a detailed description of the design process, starting from surveys and collecting and processing data, and collecting road history and other earlier data from databases and maps and so on. Then doing the analysis and diagnosis for the problems reasons, and then there is described the design process itself. Quite there are many phases in that, and that's described in detail. The lesson also gives some special design issues with paved roads. What should be done in some special with some special problems, and also special design issues with gravel roads and forest roads, such as that the wearing course of a gravel road, it should be removed always before adding new layers on the top, and things like that. And that lesson also presents techniques again, material treatment techniques against permanent deformation, such as different kind of stabilizations, and also the use of so-called non-conventional treatment agents that can improve the material quality. Okay, thank you. That was my part of the webinar, and now I will give turn to Pauli Kolisoja, the professor at the research center Terra in Tampere University, and
okay, Pauli, are you there? Or? I'm here. Shall I
Hi.
start right away,
Okay.
or is there
Yeah.
questions to Petri?
Or how should we